66 million years ago, there was a morning just like any other. Somewhere in what is now Mexico, a herd of hadrosaurs moved through a forest at the edge of a warm, shallow sea. The air was thick and humid. Insects buzzed in the canopy above. A tyrannosaur, somewhere in the distance, was doing what tyrannosaurs did, hunting, or resting, or simply standing in the heat of a Cretaceous dawn. Nothing about that morning suggested it would be the last. The world had been running the same way for over 160 million years. There was no reason to think it would ever stop. And then, from the direction of the sky, came something that wasn't supposed to be there. It crossed the entire diameter of Earth's atmosphere in less than 10 seconds. By the time anything on the ground could have registered it, if any creature had eyes fast enough, senses sharp enough, it had already hit. The explosion that followed released more energy than all the nuclear weapons ever built combined, detonated simultaneously. In the first minute, a region larger than France ceased to exist. In the first hour, the planet was on fire. In the first year, 3/4 of all species on Earth were gone. This is the story of that morning. Not the myth, not the movie version. The actual science of what happened, reconstructed from rock cores drilled out of a buried crater, from fossil beds that recorded the impact in real time, from a thin layer of clay in the Italian hills that a geologist noticed in the 1970s and couldn't explain. Minute by minute, layer by layer. The last day of the age of dinosaurs. If this is the kind of science that pulls you in, the real mechanics of how the world changes in an instant, subscribe and hit the notification bell. Every week we go this deep. You won't want to miss what's coming. Now, let's go back. 66 million years ago, Earth was a warmer planet than the one you live on now. Not slightly warmer, dramatically warmer. There were no ice caps at the poles. Sea levels were somewhere between 100 and 200 feet higher than today, which means the geography of the planet looked almost nothing like a modern map. The Gulf of Mexico reached much further inland. What is now the American Midwest was flooded by a vast, shallow body of water called the Western Interior Seaway, a warm, nutrient-rich inland sea that divided North America in two, stretching from what is now the Arctic Ocean all the way down to the Gulf. On its shores and in its waters lived creatures that had no modern equivalents. The late Cretaceous was, in almost every measurable sense, a world at the peak of its complexity. The forests were lush, conifers, ferns, and the relatively new flowering plants that had only been spreading for about 50 million years. In North America, hadrosaurs moved in herds, some of them 30 feet long. Triceratops were a common sight at the edges of forests, grazing in groups the way bison once grazed across the Great Plains. In the waterways and coastal shallows, mosasaurs, marine reptiles the size of school buses, ruled the water column. Pterosaurs with wingspans wider than a small aircraft glided overhead. And over all of it, at the top of every food chain that mattered on land, stood the tyrannosaurids. Tyrannosaurus rex was not an ancient animal by the standards of the Cretaceous. It had only evolved around 2 million years before the end of the era, which, in geological terms, makes it practically a newcomer. But it was effective. It was built for one thing, and it did that thing extraordinarily well. On the morning of the last day, individual tyrannosaurs were alive and doing exactly what they had always done, in forests that had existed for millions of years, under a sky that gave no warning. The atmosphere that morning was 20% oxygen, similar to today. The sun rose and set. Seasons changed. Droughts came and went. Volcanoes in what is now India, the Deccan Traps, had been erupting for hundreds of thousands of years, slowly pumping sulfur and carbon dioxide into the air, nudging temperatures and disrupting ecosystems gradually. Some researchers believe the Deccan eruptions had already been stressing the diversity of dinosaur species in the final few million years of the Cretaceous. The world was not perfectly stable, but it was surviving. It had survived ice ages, volcanic episodes, shifting continents, sea level changes that make modern climate variation look trivial. The dinosaurs had been through all of it. They had been through worse. There was every reason for them to keep going. That is what makes what happened next so extraordinary. Not that the world ended. Worlds, in the biological sense, end all the time. What makes this particular ending so striking is the speed. Not millions of years, not thousands, minutes. The transition from a planet ruled by non-avian dinosaurs to a planet where they no longer existed happened, in its essential trigger, in less time than it takes to watch a television episode. But to understand how we know any of this, how we can describe that morning with this level of detail, you need to follow a different story first. A story that begins not in Mexico, 66 million years ago, but in a small town in the Umbrian hills of central Italy in the early 1970s. There's a road cut near the medieval town of Gubbio, in a gorge carved by the Botticone stream. The walls of that gorge are made of pale pink limestone, layer after layer of it, deposited over tens of millions of years on the floor of an ancient sea. A young geologist named Walter Alvarez was working there in the mid-70s, studying the magnetic properties of those limestone layers, trying to understand how ancient ocean currents had moved. It was detailed, unglamorous fieldwork. He wasn't looking for anything dramatic. And then he noticed something strange. Between two layers of limestone, one from the Cretaceous, one from the layer above it that belonged to the Paleogene period, there was a thin band of clay. Not thick, about a centimeter, maybe a little more. In geological terms, a centimeter is nothing. It represents a tiny slice of time. But that band of clay was different from anything in the limestone above or below it. It was dark. It was chemically unusual. And it sat precisely at the boundary between the age of dinosaurs and the age after them. Every fossil below that clay band was Cretaceous. Every fossil above it belonged to the new world that came after. In the clay itself, almost nothing lived. Walter Alvarez brought samples home. His father, Luis Alvarez, was a Nobel Prize-winning physicist at Berkeley, not a geologist, not a paleontologist, a physicist. And he had access to analytical techniques that most geologists didn't. They ran the clay through neutron activation analysis, a method precise enough to detect elements in concentrations of parts per billion. What they found stopped them cold. The clay was saturated with iridium. Iridium is one of the rarest elements in Earth's crust. On this planet, it sank into the molten core billions of years ago, when the Earth was still forming. What little iridium exists near the surface came mostly from slow, steady accumulation of cosmic dust, microscopic particles raining down from space, year after year, century after century. In normal rock, you find iridium in trace amounts that reflect millions of years of that slow cosmic rain. In the Gubbio clay layer, the concentration was 30 times higher than anything that could be explained by background cosmic dust alone. Luis and Walter Alvarez published their findings in 1980 in the journal Science. Their conclusion was straightforward, and by the standards of geology at the time, completely radical. A large extraterrestrial object had struck the Earth 66 million years ago, and the iridium anomaly was the chemical fingerprint of that impact, scattered across the planet in a thin, global layer as the vaporized impactor was distributed through the atmosphere and eventually rained down as dust. The scientific community did not immediately applaud. Paleontologists pushed back hard. For decades, the dominant view of the dinosaur extinction had been that it happened gradually, that these animals declined slowly over millions of years due to changing climates, shifting sea levels, volcanic activity, perhaps some combination of factors that accumulated over long stretches of time. The idea that everything ended because of a single rock from space felt too simple, too violent, too fast. One prominent paleontologist at the time reportedly called the Alvarez hypothesis a physicist's solution, meaning that someone outside the field had jumped to a dramatic conclusion without properly understanding the complexity of the fossil record. But the iridium anomaly didn't go away. Researchers started looking for it everywhere, and they found it everywhere, in the same thin clay layer, at exactly the same geological horizon, on every continent, at the bottom of every ocean. Dozens of sites, then hundreds. The layer was global. Whatever had deposited it had reached every corner of the planet simultaneously. That's not what a volcano does. That's not what a slow climate shift does. That is what a massive impact does. The question stopped being, was there an impact, and became, where did it hit? The answer was already buried underground, in a place where no one had thought to look, waiting to be discovered. It sat beneath hundreds of feet of sediment and seawater, off the coast of the Yucatán Peninsula in Mexico. It had been partially identified by oil company geophysicists in the 1970s. They had detected an anomalous circular structure while doing petroleum surveys, but its significance hadn't been recognized. In 1991, geologists working with Alan Hildebrand formally identified the structure as an impact crater and connected it to the KPG boundary layer. They named it Chicxulub, after a nearby town. The crater was enormous. Not large for an impact crater enormous. Enormous in a way that takes a moment to process. The main crater structure is approximately 180 kilometers in diameter, roughly the distance from London to Paris or from New York to Philadelphia. The original transient cavity carved by the impact reached depths of around 20 to 30 kilometers into the crust. And this wasn't sitting in some remote desert where it was easy to study. It was buried under a kilometer of Yucatan limestone, with most of it sitting under the waters of the Gulf of Mexico, invisible to anyone walking above it. Which brings us to the question that had been sitting at the center of all this for decades. What, exactly, was the thing that made that crater? The Chicxulub impactor was not a comet. The chemical evidence, particularly the ratio of certain isotopes in the iridium-rich boundary layer, points clearly to a carbonaceous chondrite, a type of stony asteroid that originates in the outer main belt between Mars and Jupiter. These are among the most primitive objects in the solar system, leftovers from its formation, relatively unchanged for 4.5 billion years. They're dark, dense, and packed with volatile compounds including water, carbon, and sulfur-bearing minerals. That last detail, the sulfur, turns out to matter enormously. We'll come back to it. The impactor was around 10 kilometers across. To make that concrete, Mount Everest, the tallest mountain on Earth's surface, reaches about 8.5 kilometers above sea level. The Chicxulub asteroid was taller than Everest, end to end, and it was moving through space at around 20 kilometers per second. That's roughly 60 times the speed of sound. It entered Earth's atmosphere at an angle of about 60 degrees to the horizon, traveling from the northeast. And that angle, it turns out, was essentially the worst possible trajectory for the creatures living on the planet below, because it maximized the volume of material blasted into the upper atmosphere. There is a sobering thought buried in the geology here. If that asteroid had struck at a shallower angle, significantly less material would have been ejected into the stratosphere. If it had hit deep ocean rather than a shallow, sulfur-rich coastal shelf, the chemical consequences would have been far less severe. If it had arrived even a few minutes earlier or later in Earth's rotation, it would have hit a different part of the surface entirely. Deep Atlantic or open Pacific, with potentially very different results. The catastrophe that ended the age of dinosaurs was not inevitable in its specifics. It depended on a precise combination of the impactor's size, composition, speed, angle, and the exact geology of the surface it struck. Change any one of those variables significantly, and the history of life on this planet might look entirely different. That is a thought that has no comfortable landing place. Sit with it anyway. The science of identifying the impactor didn't stop with the crater discovery. Researchers drilling into the chicxulub structure, analyzing the boundary clay layer from sites around the world, and modeling the impact dynamics have built a remarkably precise picture of what that rock was and what happened to it. The boundary layer itself preserves shocked quartz, grains of quartz with internal fracture patterns that only form under the extreme pressures generated by hypervelocity impacts. It contains spherules of once molten rock that solidified as they fell through the atmosphere. It contains carbon from the global wildfires that followed. And in that iridium-rich dust, it preserves the elemental remains of the asteroid itself, vaporized in the first seconds of contact and distributed across the entire planet. In 2016, an international team drilled directly into the Chicxulub crater's peak ring, the raised ridge of rock that sits inside the main crater structure, and brought up cores that recorded the first 24 hours of events in geological real time. What those cores showed was extraordinary. The rock had been so violently deformed that granite from deep in the crust had been liquefied, splashed outward, and then refrozen in positions that would have been physically impossible to reach through any normal geological process. The peak ring itself formed in minutes as billions of tons of rock behaved temporarily like a fluid, sloshing inward after the initial excavation, rising up, and collapsing outward into the ring structure we see today. Sean Gulick, the University of Texas geophysicist who led the drilling project, described it as watching geology happen at a speed that geology simply doesn't happen. And this is the thing. Every piece of evidence, the iridium layer, the shocked quartz, the crater geometry, the spherule distribution, the sulfur chemistry, all of it tells the same story. The same rock, the same morning, 66 million years ago. All that evidence, reconstructed from everything that survived, points to one specific moment, one specific place. A shallow, warm sea just off the coast of what is now Mexico's Yucatán Peninsula. A morning that looked, from the ground, completely ordinary, right up until the moment the sky turned white. And that moment was closer than anyone standing there could possibly have known. The Gulf of Mexico, on the morning of 66 million years ago, was a different kind of sea. Shallower than the modern Gulf, warmer, calmer. The water temperature at the surface sat somewhere around 80 degrees Fahrenheit, closer to a hot bath than to the ocean most people have swum in. The seafloor in the Yucatan Shelf region was made largely of carbonate rock and evaporite deposits, ancient layers of limestone and gypsum and anhydrite, saturated with sulfur compounds, built up over millions of years of tropical marine sedimentation. The water above them was clear and rich with life. Mosasaurs patrolled those shallows. Not the car-sized juveniles of the popular imagination. Adult mosasaurs in the late Cretaceous reached lengths of 40 feet and beyond, built like muscular, flattened crocodiles with flippers instead of legs and tails that moved like a shark's. They were ambush hunters, patient and precise. A mosasaur in the warm Gulf that morning would have been doing what mosasaurs always did in the early hours, moving slowly through the upper water column, waiting for something smaller and less attentive to come within range. Schools of bony fish moved in tight formation through the sunlit shallows. Ammonites, coiled cephalopods that had existed in Earth's oceans for 300 million years, drifted in the middle depths, trailing tentacles through water that carried no warning of anything unusual. Sea turtles surfaced, breathed, dived. On the beaches and coastal lowlands nearby, crocodilians basked in the early morning heat. Pterosaurs lifted off from cliff faces and rode thermals rising off the warm surface water. The sky was blue. The sea was calm. Every single thing alive in that moment had every reason to believe the morning would continue in the direction mornings had always continued. It had about 90 seconds left. At an altitude of roughly 100 kilometers, the edge of space, the boundary where the atmosphere thickens enough to begin resisting, the asteroid entered. A rock around 10 kilometers across, moving at 20 kilometers per second. The atmosphere, from the perspective of an object traveling at that speed, was not a barrier. It was barely a speed bump. But physics is physics, and the physics of an object that large, moving that fast through even a thin column of gas, produces consequences that are difficult to hold in the mind all at once. The air in front of the asteroid had no time to move aside. It compressed. Compressed air heats up. At those velocities, the compression was so extreme that the air ahead of the impactor reached temperatures hotter than the surface of the sun, tens of thousands of degrees, before the asteroid had even reached the lower atmosphere. The fireball that resulted was visible from every continent simultaneously. Not metaphorically, literally. An object burning brighter than the sun, crossing the sky faster than any sound could follow it, was visible from North America, from South America, from Europe, from Africa, from Asia, anywhere the horizon allowed a clear line of sight to the direction of the Yucatan. In North America, it would have appeared as a streak of white-hot light across the daytime sky, widening and brightening in the final seconds as the object decelerated catastrophically in the lower atmosphere. Any creature with eyes that happened to be facing south or southeast in those last 2 or 3 seconds would have seen the sky turn completely white. The asteroid struck the shallow carbonate shelf of the Yucatan at an angle of approximately 60 degrees. It did not slow down before it hit. It hit the seafloor at essentially full velocity, around 20 kilometers per second, and the energy released in the first second of contact was equivalent to roughly 7 billion Hiroshima bombs. That is not a typo. 7 billion. In the first second, the impactor punched a cavity through the crust that was deeper than the Mariana Trench. The seafloor, the asteroid itself, and hundreds of cubic kilometers of carbonate and sulfur-rich rock did not break. They did not shatter. They vaporized. Instantly. The rock turned directly from solid to gas, a superheated plasma plume that exploded outward and upward at speeds exceeding the speed of sound by a factor of more than 20. Within a radius of roughly 1,000 kilometers, a circle larger than the entire country of France, the thermal pulse alone was sufficient to kill every living thing that was above ground. Not from the shockwave, not from debris, just from heat. Like opening an oven the size of a continent. Animals in that zone did not have time to respond. The air itself caught fire. Trees ignited not from flames spreading through them, but from infrared radiation, the same way paper ignites when you focus a lens on it in sunlight, except the lens was 1 billion square kilometers of superheated atmosphere, and the timescale was seconds. In coastal waters close to the impact site, the ocean was effectively removed. Not pushed back, removed. The energy of the impact was so concentrated that the Gulf of Mexico, in the vicinity of the Yucatan Shelf, was excavated. Water that had been sitting there for millions of years was launched into the atmosphere as steam and droplets at hypersonic velocities. For a few terrible minutes, parts of the Gulf seafloor were exposed to open air for the first time in geological memory. And then the crater began to form. What the Chicxulub impact carved into the Yucatan crust is one of the strangest geological structures on the planet. It is not simply a hole. The sequence of events that produced it unfolded over approximately 10 minutes. And within those 10 minutes, the solid rock of the Earth's crust behaved in ways that have no analog in anything humans have ever directly observed. The first stage is the transient cavity, the initial hole. At its maximum extent, this cavity was approximately 100 kilometers across and up to 30 kilometers deep. The impactor effectively punched through the crust toward the mantle boundary, exposing rock that normally sits at temperatures and pressures that make it flow like a very slow liquid over millions of years. But at the moment of impact, the release of pressure from above was so sudden that deep mantle rock rebounded upward, pushing the center of the crater floor back toward the surface in a matter of minutes. This rebound formed what geologists call the central peak ring, a raised ring of hills inside the main crater structure, built not from material flowing in from outside, but from deep crust that bounced upward, like the crown of water you see when a droplet falls into a still pool. Except this particular droplet weighed 10 trillion tons, and the crown of rock that bounced up was made of granite from several kilometers below the surface. At its maximum height during the rebound phase, the central uplift may have briefly stood higher than the Alps before collapsing outward into the ring structure that exists today. The final crater structure has an outer diameter of roughly 180 kilometers and a peak ring sitting about 80 kilometers from the center, all of it buried under nearly a kilometer of carbonate sediment deposited over the 66 million years since the impact, invisible from the surface, invisible from the air, discoverable only through geophysical surveys and deep drilling. In 2016, an international team of scientists aboard a specially designed drilling platform positioned in the Gulf of Mexico drilled directly into that peak ring. They extracted cores, long cylinders of rock pulled up from hundreds of meters below the sea floor, that contained a geological record of the impact that had never been read in this kind of detail before. Sean Gulick, the University of Texas geophysicist who led the project, described what they found in those cores as a sequence of events compressed into rock in a way that should not have been physically possible. The granite that makes up the peak ring is not native to the depth at which it now sits. It originated from 6 to 10 kilometers below the pre-impact surface. In the cores, it shows the characteristic microscopic signatures of having experienced pressures measured in gigapascals, pressures that only exist deep in the crust under normal conditions, and then having been instantly decompressed as the overlying material was blasted away. The rock had been effectively fluidized, not melted, but subjected to pressures so extreme that it lost its rigidity and began to flow like a thick liquid, rising upward and then collapsing outward into the peak ring in a sequence that took, at most, 15 minutes from first contact. Above the granite, the cores preserve a layer of suevite, a chaotic rock type formed when impact melt and fragmented rock fall back into the crater after the initial explosion. Above that, a thin layer of fine-grained carbonate that was deposited in the hours and days after the impact, as the earliest material began settling back down into what was now a flooded, steaming crater basin. The entire catastrophe compressed into about 30 meters of rock. Gulick's team also found something in those cores that had significant implications for the global climate effects that followed. The sulfur content of the peak ring rocks was almost completely depleted. The carbonate and evaporite layers that made up the Yucatan shelf, those ancient, sulfur-saturated sediments, had been almost entirely vaporized. Somewhere between 100 billion and 500 billion tons of sulfur dioxide was injected into the stratosphere in the first seconds of the impact. That number will become important While the crater was forming in Mexico, the rest of the planet was experiencing something that had no precedent in the history of complex animal life. The initial explosion launched billions of tons of vaporized and molten rock on ballistic trajectories, not just into the atmosphere, but entirely out of it. Chunks of rock, droplets of melt, streams of superheated vapor rose above the atmosphere and began arcing back down toward Earth across the entire hemisphere. As these ejecta re-entered the atmosphere, coming in from above, from every direction, like a continuous bombardment from space, they heated the upper atmosphere by friction in a way that had nothing to do with the original fireball. Think of a meteor burning up in the atmosphere on a clear night, a bright streak, a brief glow. Now multiply that by billions. Billions of particles, ranging from microscopic glass spherules to chunks the size of boulders, all re-entering simultaneously from every point of the compass. The cumulative heating from this re-entry was estimated by some models to have raised the temperature of the upper atmosphere across the entire planet to several hundred degrees Celsius within the first hour. Not at ground level, at altitude, in the atmosphere itself. But the infrared radiation radiating downward from that heated air reached the surface as a pulse of intense heat lasting somewhere between 15 minutes and an hour. 15 minutes to an hour of infrared radiation intense enough to ignite dry vegetation spontaneously. On every continent, simultaneously. There is no gentle way to frame this. In the first hour after impact, every forest on Earth with dry enough surface material, and in the late Cretaceous, that meant enormous areas of North America, Asia, and Europe, began to burn from the top down, ignited not by flames spreading from tree to tree, but by the sky itself, radiating heat like the inside of a broiler. The fires did not start at one point and spread outward. They started everywhere at once, like the planet had been placed under a grill. Geological evidence for these fires exists in the boundary layer at sites around the world. Soot, charcoal, polycyclic aromatic hydrocarbons, all concentrated at exactly the KPG boundary horizon. Researchers analyzing boundary clay from sites in Europe, North America, and the Pacific found soot concentrations consistent with the burning of roughly 70% of the world's above-ground biomass. That is not a worst-case estimate. That is what the chemistry in the rock actually shows. The fires would burn for months, and back in the Gulf of Mexico, the sea was returning. The impact had pushed the water outward in every direction simultaneously, a displacement wave unlike anything the modern ocean has ever produced. The closest modern analogy is a tsunami from a submarine earthquake, but the comparison barely works. Earthquake tsunamis are generated by a displacement of the sea floor over an area of hundreds of square kilometers. The Chicxulub impact displaced the sea floor over an area of thousands of square kilometers, instantly, with an energy release roughly 1,000,000 times greater than the largest recorded earthquake. The initial wave height in the immediate vicinity of the impact was estimated at several kilometers. Not meters, kilometers. As this wall of water radiated outward across the Gulf of Mexico and into the Atlantic, it lost height but gained breadth, becoming a series of massive waves hundreds of feet tall. Coastal North America, coastal South America, coastal Europe, coastal Africa. All of them were struck by wave trains that traveled inland for tens of miles, scouring everything in their path down to bare rock. At the speeds these waves traveled across open ocean, the farthest coastlines were not reached in hours, but in something closer to half a day or more, 12 to 20 hours for the most distant shores. The impact was instantaneous. The ocean's response was not. And then, in 2012, a paleontologist named Robert De Palma started excavating a site in North Dakota, a place called Tanis. that would eventually provide the most direct evidence yet of what those first hours looked like from the ground. Tanis sits in the Hell Creek Formation, a geological unit famous for its late Cretaceous fossils. But what De Palma found at Tanis was different from a typical fossil site. The deposit was not a gradual accumulation of bones and sediment over thousands of years. It was a single event layer, a tangled mass of fish, trees, insects, and other organisms, all buried together in a chaotic mixture of sand and fresh water, deposited in what appeared to be a matter of hours. The fish in the deposit were paddlefish and sturgeon, freshwater species, not marine animals. But they had died with tiny glass spherules embedded in their gill arches. Those spherules were impact ejecta, the same tiny glass droplets that form when molten rock is sprayed into the atmosphere at high velocity, cools rapidly, and falls back to Earth as glassy beads. The fish had been alive and actively breathing when the spherules began raining down, early enough after the impact that their gills were still filtering water, which means they died within the first hour or two of the impact. What killed them was not the spherules themselves, but the water. The impact generated seismic waves, not tsunamis, but ground-shaking waves traveling through the crust, moving at the speed of seismic energy that reached North Dakota within minutes. Those seismic waves caused a phenomenon called a seiche in the shallow inland waterways of the Hell Creek region, a sudden, violent sloshing of water, like shaking a bathtub. The seiche surged back and forth, repeatedly inundating the riverbanks and depositing fish and plant material together in chaotic layers before the water finally settled. All of this happened before any ejecta had reached the site. The spherules in the fish gills were falling out of the sky while the seiche was still active. De Palma's Tanis site is, in a sense, a snapshot of the first 2 hours of the worst day in the history of complex animal life on Earth. The fish captured there didn't survive long enough to see the sky darken. They didn't live to feel the cold. They died in the first violent shudder of a planet absorbing an impossible blow, buried under a wave of churned fresh water, while glass beads rained down from a sky that was still blue, but filling, very slowly, with something that the world had never seen before in the quantities now entering it. Something that would prove, in the months and years ahead, to be just as lethal as the fireball itself. The sky above North America went dark before the fires had finished burning. Not gradually, not the way dusk settles in stages, giving eyes time to adjust. The darkness came from above, from the stratosphere, where billions of tons of soot and pulverized rock and sulfur dioxide were spreading outward from the impact point in every direction, carried by high-altitude winds that circled the globe. Within days, the particulate cloud had covered the northern hemisphere. Within weeks, it had reached the southern hemisphere. Within 2 months, the entire planet was under a canopy of dust and soot so thick that the amount of sunlight reaching the surface dropped to somewhere between 1 and 10% of normal levels. 1 to 10%. On a clear day, you get full sunlight. In the months after Chicxulub, the surface of the Earth received something closer to what you'd find in a very deep forest on a heavily overcast day. Not pitch black, but dark enough that photosynthesis, the process on which almost every food chain on the planet ultimately depends, slowed to a near stop. The temperature dropped fast. Models built from physical principles, the same models used to study the effects of large volcanic eruptions and nuclear exchange scenarios, suggest the global average surface temperature fell by somewhere between 15 and 25 degrees Celsius within the first year. In continental interiors, the drop was steeper. Rivers and lakes that had never frozen in the warmth of the late Cretaceous began to ice over. Tropical forests that had survived for millions of years in stable equatorial warmth suddenly found themselves in conditions closer to a cold, temperate winter, and they had no adaptation for it. None. Evolution cannot prepare an organism for a catastrophe that has never happened before. There is a researcher whose work sits at the center of our understanding of this cold and dark period. His name is Pim Kuiper, a Dutch paleoclimatologist who spent years analyzing pollen records from sediment cores taken at sites across Europe and North America, looking at the layers directly above the KPG boundary. Pollen is extraordinary evidence. A single gram of ancient sediment can contain thousands of pollen grains, each one a precise identifier of the plant species that produced it. And pollen is nearly indestructible. It survives millions of years in the right conditions, preserving a record of the plant communities alive at any given moment. What Kuiper and his colleagues found in cores taken from boundary sites was a story told in absences. Below the iridium layer, the pollen record was rich and diverse. Dozens of species, a complex mix of conifers, flowering plants, ferns, palms. At the boundary itself, most of those species vanished from the record. Simultaneously, in a geological instant. Above the boundary, the layers representing the first years after the impact, the pollen record was dominated by a single group. Ferns. Just ferns. Fern spores are among the first colonizers of devastated landscapes. They appear in enormous quantities after volcanic eruptions, after fires, after any event that strips a landscape bare. The fern spike in the KPG boundary record is global, found at sites in North America, Europe, New Zealand, South America, and it represents something specific. A world where almost everything that had been growing before was dead or dying, and the only plants capable of exploiting the ruined landscape in any numbers were the simplest, most resilient ones. The fern spike lasted, in some regions, for tens of thousands of years. That is how long it took for complex plant communities to begin reassembling themselves. Now think about what that means for an animal that weighs 6 tons and eats nothing but plants. A triceratops in the weeks after the impact would have been experiencing something that had no name in the world it had evolved in. The ferns and cycads and flowering plants it depended on had been scorched by weeks of fire and then left in near total darkness. The ground that had always produced food was producing less of it every day. A triceratops could not reduce its metabolic needs the way a small mammal could. It could not hibernate. It could not shift its diet to insects or fungi in any meaningful way. It needed enormous quantities of plant material every single day to sustain a body built for a world that no longer functioned the way it always had. And it was cold. Not catastrophically cold by Antarctic standards, but cold in a way that the late Cretaceous had not been cold. A sustained, months-long chill in regions that had been tropical or subtropical for millions of years. The insects that pollinated plants struggled. The plants that depended on insects for pollination failed to reproduce. The herbivores that depended on those plants began losing body condition, and the predators that depended on those herbivores followed, a few weeks or months behind. The collapse was not instantaneous. It cascaded. Like a structure where the load-bearing elements are removed one by one, each removal slightly manageable, until the cumulative deficit becomes unsurvivable. Large herbivores were among the first to go, simply by arithmetic. A single adult hadrosaur consumed hundreds of pounds of vegetation per day. When that vegetation disappeared, the animal had weeks, not months, before starvation became fatal. Sauropods, the long-necked giants that still persisted in some parts of the world in the late Cretaceous, faced the same equation. The largest animals on the planet needed the most food, and food was disappearing fastest. The marine reptiles, mosasaurs, plesiosaurs, faced a different version of the same arithmetic. The cooling of surface waters and the collapse of phytoplankton, the microscopic algae that form the base of marine food chains, and which are as dependent on sunlight as any land plant, destroyed the foundation of the ocean's productivity. The process unfolded more slowly in the ocean than on land, because marine food chains have more layers of buffering between the base and the apex. But it worked. By the end of the first year, large marine reptiles were functionally extinct across most of the world's oceans. The pterosaurs, those extraordinary flying reptiles with wingspans ranging from the size of a sparrow to wider than a small aircraft, needed insects and fish to survive. Both were collapsing, and pterosaurs, despite their ability to fly, could not cross the darkness. There was nowhere to fly to. The darkness was global. And then there was the issue of reproduction. Many large reptiles laid eggs. Eggs incubate in warm soil. When the temperatures dropped and the soil cooled, incubation times lengthened, and in some cases the eggs simply failed to develop. A species cannot maintain a population if its young stop surviving. Even populations that had enough adult individuals to weather the food shortage ran into this wall. A generation gap, a period when no young are successfully raised, is manageable for a short-lived animal that reproduces quickly. For a species with a generation time of 20 or 30 years, a gap of even 5 years in successful reproduction is catastrophic. Non-avian dinosaurs, by the best estimates from bone growth studies, had generation times measured in decades. They did not get 5 years. They got the darkness, and the cold, and the collapse of the food chain, and they did not come back. But some things did. In the same Hell Creek Formation where paleontologists have found the bones of Tyrannosaurus and Triceratops and hadrosaurs, they also find the bones of something much smaller, much less impressive looking. Small insect-eating mammals that spent their lives burrowing underground and coming out primarily at night. A behavioral adaptation forced on early mammals by 100 million years of living in a world owned by dinosaurs. A paleontologist named Tyler Lyson, working at the Denver Museum of Nature and Science, spent years excavating sites in the Hell Creek and early Paleocene layers of Colorado's Corral Bluffs, a Badlands site that had been largely dismissed as unproductive by previous researchers because the fossils were encased in concretions of iron-rich rock. Lyson had a realization. Those same concretions that made the fossils hard to see on the surface were also protecting them. He started cracking open concretions in the field, and what he found inside changed the picture of post-impact recovery significantly. In the earliest Paleocene layers, the rock representing the first few 100,000 years after the impact, the mammals he found were small. Very small. All of them under a kilogram. Insect eaters and seed eaters, with teeth adapted for hard, dry food that survives in soil long after green vegetation has died. As he moved up through the layers, tracking the first million years after the impact, the mammals got larger. Not dramatically, not overnight, but measurably, consistently larger, with more diverse diets, more diverse body plans. The recovery was happening in the rock, preserved as a gradient of bones getting gradually bigger and more varied as the centuries passed. The reason these small burrowing mammals survived while the dinosaurs didn't comes down to several converging factors, that all connect to the same underlying logic. Small bodies need small amounts of food. A creature the size of a shrew can get by on insects, seeds, fungi, and decaying organic matter, all of which remained available even after photosynthesis had effectively stopped, because decomposition doesn't need sunlight. Burrows provide thermal insulation. An animal underground is buffered from the violent surface temperature swings that the months after chicxulub produced. And short generation times meant these animals could adapt, behaviorally and eventually genetically, far faster than creatures that spent decades between birth and reproduction. It was not the strongest that survived chicxulub. It was the smallest, the most flexible, the most willing to eat almost anything. Evolution, compressed into a geological moment, selected ruthlessly for precisely the traits that would, 66 million years later, produce the diversity of mammals that now dominates the planet, including, eventually, us. Now, there is a dimension of this story that doesn't sit in the geological record. It sits in the arguments of scientists who spent decades fighting over what the record actually means. And one of those arguments became one of the most heated disputes in modern paleontology. Walter Alvarez and his father Luis had proposed in 1980 that a single impact caused the mass extinction. Their iridium anomaly was real, their evidence was growing, and by the early 1990s, the discovery of chicxulub had given their hypothesis a physical location to anchor it. For most researchers in the field, the debate was effectively settled. But not for Gerta Keller. Keller was a paleontologist at Princeton, and she had spent decades working on the precise stratigraphy of the KPG boundary, the detailed ordering of rock layers and the fossils within them at sites in Mexico, India, and around the world. Her reading of the evidence was different, and she was not quiet about it. At conferences through the 1990s and 2000s, Keller argued that the chicxulub impact had occurred not at the KPG boundary, but approximately 300,000 years before it. That the crater predated the extinction event by a significant margin, and that the actual killing mechanism was the Deccan Traps volcanism in India, which had been erupting for hundreds of thousands of years and which, in her view, had already driven biodiversity to a breaking point before any asteroid arrived. The argument was not a minor technical disagreement. It went to the heart of how mass extinctions work, whether they are triggered by single catastrophic events or by accumulated stress over long periods of time. And it was conducted at times with a sharpness that went beyond normal scientific debate. Keller's reinterpretation of the chicxulub stratigraphy, her argument that the crater sediments had been misread, that the boundary layer at the impact site was not contemporaneous with the global extinction, was rejected by most researchers in the field, often forcefully. At a Geological Society meeting in the early 2000s, an exchange between Keller and several impact researchers became something of a legend in the paleontology community, not because anyone said anything unprofessional, but because the divide between the two positions had become so complete that the two sides were effectively working from incompatible interpretations of the same physical evidence. Keller pointed to foraminifera, tiny single-celled marine organisms that she found surviving in sediment layers she argued post-dated the impact. The impact researchers pointed to dating methods they said conclusively placed the crater at the boundary. Each side believed the other was making a fundamental error in reading the geology. The weight of evidence, as it has accumulated through the 2000s and into the present decade, has moved decisively in one direction. High-precision radiometric dating of the chicxulub impact melt, zircon crystals from the impact layer dated using uranium-lead decay, places the impact within 40,000 years of the KPG mass extinction boundary. Given the resolution of geological dating at 66 million years, 40,000 years is effectively simultaneous. The Deccan volcanism was real, and may have contributed to pre-existing ecological stress, but the impact was the hammer. Keller has not fully recanted her position, and in a narrow scientific sense, that's not unusual. The history of geology is full of researchers who held minority positions for decades. What the Keller controversy did, in a practical sense, was force the pro-impact community to be far more precise in their evidence, to drill deeper, to date more carefully, to leave less ambiguity in the record. The drilling of the Chicxulub peak ring in 2016, which produced the clearest, most direct evidence yet of the impact's simultaneous timing with the boundary, was partly a response to a field that had been challenged to prove its case more rigorously than it thought necessary. Science sometimes advances by being argued at. And Gerda Keller, whatever the final verdict on her specific claims, made the argument uncomfortable enough that the answers that emerged were better than the ones that existed before she asked the questions. Now stand up from that argument. Walk away from the conferences and the cores and the clay layers. Let 66 million years pass in the space of a few seconds. The first century after the impact was the quietest the Earth had been in hundreds of millions of years. The forests were gone. The great herbivores were gone. The predators that had lived on them were gone. The pterosaurs were gone. The mosasaurs were gone. The ammonites, those coiled cephalopods that had drifted in Earth's oceans since the Devonian, 300 million years before, were gone. Completely. Not one species survived. What remained was a scorched and cooling planet populated by small things. Insects hiding in soil. Seeds lying dormant in the ash. Fern spores waiting in the dark. Small burrowing mammals eating whatever could be found underground. Freshwater turtles that could survive on decaying organic matter at the bottom of cold rivers. Crocodilians doing what crocodilians have always done, which is essentially waiting, cold-blooded, metabolically flexible, able to go months without food. Sharks in the deep ocean, circling in darkness below the surface layer where the productive zone had collapsed. The ferns came first. Then, slowly, the flowering plants began to recolonize the bare ground. Insects followed the plants. Seed-eating birds, the only surviving dinosaurs, the avian lineage that had split off before the impact, began diversifying. And the mammals, feeding on seeds and insects, began to grow. Not quickly, not in any way that would be visible on a human timescale. In the first million years of the Paleocene, the largest mammals on Earth were still small, roughly the size of a house cat. But the trajectory had changed. The constraint that had kept mammal size down for 160 million years, the presence of large, ecologically dominant dinosaurs in every terrestrial habitat, was gone. The ecological space that had been locked up for eons was suddenly, catastrophically open. And evolution, given open space and time, fills it. By 30 million years after the impact, the first large mammals were evolving. By 50 million years after, the ancestors of whales had entered the ocean. By 60 million years after, the primate lineage had split off, small, tree-dwelling creatures in tropical forests with forward-facing eyes and grasping hands, living in a world that still bore the geological scars of Chicxulub in its rock record, but had, in every living sense, been remade. And then, 66 million years after that morning in the Gulf of Mexico, one of those primates developed the capacity to look at a layer of clay in a hillside in Italy and ask, "What happened here?" You are the answer to that question. Not metaphorically, literally. The particular set of evolutionary pressures that produced the brain you are using right now to follow this story began with the survivors of Chicxulub. The mammals that hid in burrows while the sky was a broiler and the forests were ash were your ancestors in the most direct biological sense.
If the asteroid had missed,
If it had passed Earth by even a fraction of a degree in its orbital trajectory, a margin that could have been provided by the gravitational influence of any number of other bodies in the solar system, the mammals might never have had the ecological space to grow and diversify. The dinosaurs might still be here, filling every large terrestrial niche on every continent, and the small, skulking, nocturnal primate ancestor that eventually became you would still be small and skulking and nocturnal in a world that belonged to something else. There is a moment that I keep coming back to. Robert De Palma, standing at Tanis in the Hell Creek Badlands of North Dakota, cracking open a concretion of rock with a geological hammer and finding inside it a paddlefish, a freshwater fish that died in the first hour of the worst day in animal history, with glass spherules in its gills, buried by the Seiche wave before the sky had even finished filling with dust. That fish has been inside that rock for 66 million years. It has been inside that rock since before our entire mammalian lineage had learned to be anything other than something small and frightened that lived underground. De Palma lifted it out of the rock with a brush. And somewhere in the lineage between that frightened, burrowing ancestor and the person holding that brush, you happened. You. And everything that makes human existence possible. Language, science, curiosity, the capacity to look at a layer of iridium in a hillside and spend 50 years figuring out what put it there. The asteroid that killed the dinosaurs didn't just end one world. It started the chain of events that built yours. Next time you walk outside and look up at the sky, clear blue or full of clouds, or dark and full of stars, remember that you're standing on a planet that has been here long enough to be almost completely remade by a single morning. That what feels permanent and stable, the ground under you, the air around you, the life filling every corner of the world you can see, is the outcome of a catastrophe. Rebuilt, slowly, by the smallest things that survived it. That rock fell 66 million years ago. You are what grew from the silence that followed. If this is the kind of science that changes the way you see the world around you, subscribe. We go this deep every single time. And share this one with someone who still thinks the dinosaurs just slowly faded away. They deserve to know what actually happened.